Hi, my name is David, and today I'm going to be talking about rigid body dynamics. Using particular methods, we can analyze and try to find the motion of any point within a rigid body. The three methods that I will discuss are balance laws, impulse momentum, and work energy. First, I will talk about the use of balance laws. To solve problems using translational motion, we already can use Newton's second law, F equals ma, meaning that the sum of the forces or net force acting on a body will be equal to the product of mass and linear acceleration. Note that this only refers to the force acting on the center of mass of the body, as well as the acceleration of that center of mass. For problems involving rotational motion, we use the equation for the balance of angular momentum, mg equals ig alpha. This means that the sum of the moments, or net moment, about the center of mass of a body is equal to the product of mass moment of inertia for that center of mass and angular acceleration. If we want to sum moments about a fixed point O that may or may not be the center of mass, we can use MO equals IO alpha. However, if it is more convenient to sum moments about a different point P, then we use a different equation. MP equals IP alpha plus R g with respect to P cross product MAP. This equation simply accounts for the relative motion between G and P. Now that we have translational and rotational equations, we can use relative motion to combine the two equations to give total motion. I realize that this is a rather scant explanation of the use of balance laws, and a lot of practice is required to familiarize yourself with questions. I won't actually do any examples here, because to go through a sufficient number of examples would take far too long. Go to your tutes! Next, I will talk about the impulse momentum method. Impulse is defined as the product of average force and the time over which the force is exerted. Impulse can be found as the integral of the sum of external forces with respect to time. Linear momentum is defined as g equals mv. If we differentiate g with respect to time, we get the derivative of mv with respect to time, which is simply ma. So, for a body that does not change mass, ma is the rate of change of linear momentum, or dg dt. Knowing that force is equal to ma, we can see that integrating the force with respect to time will give us the product of m and the change in v, which is the change in linear momentum. We also know from our definition that the integral of force with respect to time gives the impulse, so we can say that the impulse exerted on a body is equal to the total change in linear momentum of that body. Note that all this analysis can also be applied to angular motion. Angular momentum about a point O can be defined as HO equals IO omega. If we carry out similar calculations as before, we find that MO equals IO alpha, and the integral of MO equals IO omega. Using these two equations for angular and linear momentum, we can analyze the motion of the body. Note that as a result of using impulse momentum, we know that momentum is constant in the absence of external forces, which is useful when analyzing systems of rigid bodies. Finally, I will discuss the work-energy method. This method uses the assumption that the total work done on or by a system or body is equal to the change in mechanical energy of that system or body. The total work is the sum of the work done by forces and the work done by moments. The work done by forces is given by the product of force and change in distance, while the work done by moments is given as the product of moment and change in angle. The sign convention of the work depends on the direction of motion of the body and the direction of the force acting on that body. If the force or moment is acting against the direction of motion, then the work done is negative, and vice versa. A simple example of this is friction, in which case the work done is negative, because it always opposes the direction of motion. When using work energy, we equate this work term with the change in mechanical energy. The total change in mechanical energy is found as the sum of the change in kinetic energy T, the change in gravitational potential energy Vg, and the change in elastic potential energy Ve. When finding the change in kinetic energy, there are two terms, the translational kinetic energy and the rotational kinetic energy. These are given as half m v2 squared minus v1 squared and half I omega 2 squared minus omega 1 squared, respectively. I won't go into the very lengthy proof here, refer to lecture notes on Samuel Koenig, but it is important to note that when the motion of a body is purely rotational about a point that is not the center of mass, then you can still ignore the term for translational kinetic energy. In this case, make sure to use the parallel axis theorem when finding the moment of inertia about the new point of rotation. The change in gravitational potential energy is very simply given as mg h2 minus h1. The change in elastic potential energy is given as half k x2 squared minus x1 squared. Note that x is the difference between the current length and the unstretched length, so finding the unstretched length of the spring is required unless it is given. Now that we have equations for the work done, as well as the change in mechanical energy, we can simply equate them. I hope that you found this useful for understanding rigid body dynamics. Again, a lot of practice is required. Good luck and have fun.